So thanks a lot for this nice introduction. Also, I'm very honored to be here, so to also join this wall of fame that Paulo was showing this morning in the Meta-optics session. So I will not be talking about tera-earth. I will be talking about metasurfaces and mainly focusing in the optical regime. So these are the type of structures that I would like to discuss over this, this 50 minutes, right? So these are arrays of metallic or dielectric nanoparticles. So we work, or what I will be mainly showing is in the visible, right? So at optical frequencies. We also have work, as Olivier has mentioned, in the tera-earth regime. So this is an example of a tera-earth metasurface. Here you see the scale bar is 200 microns, so these structures are resonant at a much longer wavelengths. However, the focus will be here in the optical regime, and well, we designed these metasurfaces to enhance light-matter interaction, to achieve a strong light-matter coupling, form polaritons, and these polaritons, they are bosons that can condense into a ground state and then have a coherent emission. So this is a condensate, a Bose-Einstein condensate, or a polariton laser. So that will be the main focus of my talk. However, I will just put it in a broader context. So when we started this work in the group some years ago, so our motivation was just to control the emission properties of single emitters, quantum emitters. And well, if you consider a dipole, well, this is a highly localized source of polarized electromagnetic radiation. And because it's highly localized in space, it will also have a highly non-directional emission, right? So you have this relation by the uncertainty principle, and this dipole emits in many directions, right? So what we want to achieve is a full control of these emission properties, right? So of optical sources. And by full control, I mean control of the emission spectrum, the efficiency of the emission, the directionality, of course, and also the polarization. Okay, the way of doing that is by coupling that emitter, that single emitter, this quantum emitter, into to a resonant structure, right? So, and the resonant structure, these are what are called optical antennas or nano antennas. And when you couple them, then you have the antenna and the emitter, right? So which form a structure which have a design properties defined by the nano antenna. Right, so you can couple these emitters to a single rod. You can have more complex structures, right? So this was the work of Alberto Kurt and Van Hulst, coupling single quantum dots into a Yagi-Uda antenna and then controlling the directionality of that emission.